Thank you so much, Aki. It's a great pleasure to be back this morning. And welcome back for those that were here yesterday, and welcome for the first time to those that are just joining us today. If you were not here yesterday, please do not worry, because even though the general subject area, we're still following it, it's dealer intermediated over-the-counter markets and market design. The specific application that we're working on today is a different one. Yesterday, I spent most of the time motivating the topic and giving you an application to markets, over-the-counter markets, in which the friction, the main friction, is the cost to the dealer of providing a space on its balance sheet to accommodate your desired trade. If you remember that, the dealer incurred some cost associated with funding to offer you a price because it's costly to the dealer shareholders to acquire your asset if you want to trade. And since the financial crisis, those costs, as I mentioned yesterday, have gone way up. And as a result, empirically, the balance sheet space devoted to market making has come down dramatically, like 80% for corporate bonds. Today, the topic is a different friction. The friction today is the fact that if you think of yourselves as potential buyers in this market, the fact that you don't know what the going price for the asset is. So if it's a bond, or if you need to borrow money, or if you need to buy a foreign currency or oil or some other asset that's traded on the over-the-counter markets, meaning by a dealer, you don't know at what price this asset is being traded. The dealers know, but you don't know. And so I think Yanung was our candidate buyer yesterday. Yanung comes to Aki, for example, who's a bank who's making markets in the asset. And Aki asks, how much would it cost today to buy a pound of gold? And Aki says, $1,100. By the way, does anybody here in this room know whether that's kind of below the market price or above the market price? Most of us don't know. Actually, I don't even know. It's below? Okay, so you're not a good candidate. You're not supposed to know. But Aki knows because he is Goldman Sachs or JP Morgan, and he knows the price. But Yanung is not supposed to know the price, and so he doesn't know when Aki says $1,100 an ounce, whether to take it or not. Maybe keep searching for a better price. It's like you're buying a new car, but you don't know what the prices of the cars are. That is a friction in markets, because now Yanung will incur search costs. He may not even enter the market if he thinks that he won't get a good price, because maybe Aki is taking advantage of him. Possibly. Or Yanung could be a very fast trader. We're going to have both fast and slow traders today. Fast traders, they know the price because they can search the entire dealer market instantly. Slow traders, no. They may not even enter the market, and if they do, they may not get efficiently matched to the dealer that has the lowest cost for providing the asset. Okay, so that's the theoretical subject for today. But before we get into that, I want to talk about the main sources of price information to you all, the investors in this market, in common practice. So a little bit of practical motivation, and then some theory. Okay? And the rules for today are the same as yesterday. Please interrupt, ask questions. I'm going to try not to rush through this material. We're going to actually go a little bit slower today because we're doing a little bit more theory. Okay? We actually have some market design theorem proof. Nobody has a question yet. Okay, so first, what are the sources of price information that Yanung might have available? Well, under US rules, and now increasingly under European rules, many over-the-counter assets, the prices must be reported within a short time after the trade occurs. Okay, this is not like an exchange where you can see the price at which everybody is trading. The individual price that Yanung and Aki agree on need not be reported to everyone. But under current rules, there's an increasing tendency. So in the corporate bond market, there's a new system called TRACE that requires the price to be reported within a few minutes. Many other assets, that's not the case. For example, you might be surprised to know that for US Treasury bonds, there is no such requirement. It's a completely dark market except for the dealers. A second source of price information is what's called pre-trade price transparency, which means when Yanung is asking for the quote, he can see, let's say this row of market participants are also dealers, he can see the prices in which they are offering on the platform. We're not going to do that extension today, but it is possible. In fact, I gave it to my students at Stanford as a final exam question last year. So everything I'm going to say today will extend to the multi-dealer platform price quotations. But today we're going to do one dealer price quotations. But that's another source of price transparency because in the multi-dealer platform, Yanung can see the prices offered by at least 1, 2, 3, 4, 5, 6, 7 dealers in the market. That's a lot of price information. And that will force the dealers to compete more fiercely to get his trade because they all know that if they don't give Yanung a good price, he won't buy. So they're going to bid more competitively, the market will work more efficiently. Okay? The third source of price information is the one I'm going to focus on today, and it's called benchmarks, which means that some publishing service will print, perhaps once a day, an estimate of the interdealer market price, the price that the dealers must pay to acquire the asset. So if it's gold, there is actually a daily fixing that's set in a small auction among the dealers, and it's published. And now when Yanung calls Aki and asks for a quote, he knows the, let's say, average dealer price. And if Aki tries to take too much advantage by quoting a much higher price, then Yanung will say, no, I'm going to keep searching to the other dealers in this row until I get a price that's closer to the average dealer price. And since Aki knows that Yanung has this option, Aki will bid more competitively and the market will work more efficiently. And that's the main result for today, which is if you have a published price that's the, let's say, average dealer cost or typical dealer cost, then the market will be more efficient. We know that this is important in practice because there has been a lot of controversy about the quality of the reporting of these benchmarks. How many have heard of LIBOR? Show of hands. Okay, many. LIBOR, as you know, was manipulated. So was Euribor, which is the European version of LIBOR. So was TIBOR, the Tokyo interbank offered rate. These are benchmark interest rates. They're not the cost to Aki for lending, but they're the average cost to the dealers for borrowing and lending in the interdealer market. Likewise, we have overnight interest rates like SONIA and Ionia. Those are benchmarks. We have foreign exchange fixings, 4 o'clock every afternoon. There is within a short time window of 5 minutes. They average the transactions prices. That number is reported. For gold, silver, palladium, platinum, these are all available benchmarks where the average dealer price is reported, let's say, once a day. Likewise, in the oil, natural gas, iron ore, many other commodities markets, there's an average dealer price reported once a day. And many other contracts, like futures contracts and other derivatives, or bond contracts, or equity contracts, or exchange-traded fund contracts, their payments to investors are determined based on these benchmarks. Likewise, for many manufactured goods, like pharmaceuticals, or cars, or used cars, there are benchmark reported prices. So the publication of these prices is information to investors that promotes market efficiency. That's the theme for today's next half hour to 45 minutes. And I want to again leave as much time as possible for discussion. This just gives you an example of the dependence of borrowing markets and derivatives markets on LIBOR, which shows, let's say in the case of US interest rate swaps, 106 trillion of derivatives contracts whose payments depend on LIBOR. It's a very important benchmark. And I'm not going to dwell on this chart because I want to get on to the theoretical applications. By the way, all of these benchmarks and many others were manipulated. They were misreported on purpose to deceive investors in various ways and for various purposes. And there's been a lot of, I'll just close that door. Oh, it's already closed. There's been a lot of penalties and fines that have been paid by the dealers for manipulating those prices. And that means that the price transparency that Yanung has been relying on could be reduced in quality, and that reduces the efficiency of the market. Okay, so but that's not our topic today. I actually have some other work with Piotr Dvorak on the design of benchmarks that are resistant to manipulation. So that's a new topic of research, but that's not for today either. Okay, so for today, I'm going to focus on one model instead of skipping across a lot of different things. And the one model is the implications for benchmark transparency, that is for providing a benchmark. So the two worlds are either we have a benchmark or we don't have a benchmark. We'll examine them one at a time, and then we'll compare the social efficiency of those two market designs. So again, this is a market design problem. And the design issue is, should you have a benchmark? And the answer is, under reasonable conditions, yes, it improves the gains from the socially efficient gains from trade, but not in 100% of the cases. There are small cases in which, or let's say, unlikely cases in which the parameters go the other way and suggest you shouldn't have a benchmark. I'll explain that later. This is joint work with the same Piotr Dvorak, who was a Stanford PhD student. Now he is at the Becker-Friedman Institute at the University of Chicago. He'll be joining Northwestern University. He's a microeconomist from Stanford. And the other co-author is Haoshang Zhu, who's a financial economist at MIT. And I've listed the three ways, the three channels by which having a benchmark will improve market efficiency in many cases. First, increasing the volume of beneficial trade through first signaling to Yanung that the price is with you. When he sees the benchmark, he knows the price that he gets will likely be good enough to bother trying to trade, to enter the market and trade. So that will increase, by providing more transparency, that will increase the likelihood that Yanung will enter the market and gain from trade. Secondly, when Yanung gains, he'll gain more because Aki has to compete harder when there's a benchmark. So Yanung will say, I'm glad there's a benchmark. That means Aki will know that I know the going price. He will have to bid more competitively. Yanung will suffer a smaller bid-offer spread. He'll lower execution cost. He'll get a better price. And that will also encourage him to enter the market. Second category, when Yanung enters the market and he finds out that maybe Aki is not giving the best price because Aki doesn't have a low-cost access to the asset, Yanung will more quickly find who in this row is going to be able to provide the asset at lowest cost. So better efficiency through reducing the number of times that Yanung has to search. In fact, in the simplest case, Yanung will be able to get a match on the first trade or not at all. So basically, he'll be able in equilibrium to enter the market and trade on the first go, or discover that it's not worth searching and leave the market. So very efficient in terms of use of search costs. And in practice, it's rarely the case that investors actually search the wide market, because everybody knows that Yanung knows that there's a benchmark, and they offer a price that's just good enough that he'll accept it. Yes?
In Diamond's original model,
yes.
Even if there is no information about price,
yes.
People stop searching in the first round. But the price is, of course, monopoly price.
Yeah.
So by...
Yeah, that's the Diamond paradox.
Yeah.
Yeah, we're going to eliminate that problem because we're going to assume that some of the investors have zero search cost.
Okay.
These are the fast investors. So when we get to the theory part, we're going to have a continuum of investors, a fraction mu of which have zero search costs, and they will discipline the investors from charging the monopoly price, overcoming the diamond paradox? That's a good question. The third way that having a benchmark will improve market efficiency is that and I think I already alluded to this, it will allow the lowest cost dealer to be more likely to provide the asset to Yunnan. So you get better matching, more efficient matching. It's not only efficient for Yunnan to be able to trade, it's also efficient for him to be able to conduct a trade with the lowest cost dealer. That's socially efficient. And more transparency helps here, because when he calls Aki and Aki gives a high price, Yunnan says, I know the benchmark. I see his price is high. He must be a high-cost dealer. I'm going to keep searching until I find a more efficient match. And that improves social gains. Remember, the prices, both yesterday and today, the prices themselves are not the sign of efficiency, because that's a mere transfer. What really matters is that when there's a gain from trade, it's realized, and that the gain from trade is maximized by best matching. And that's very similar to the motivation that Fujita gave yesterday. Okay? There is some related work on transparency in search-based markets. For example, in a macroeconomic context, Benabou and Gertner, we're going to be moving one step ahead from a precursor model that comes from Janssen, Pichler, and Weidenholzer, which itself is an advance on a famous 1989 paper by Stahl. So we're just moving the ball one step forward, but we're moving it out of the context of goods markets and into the context of financial markets, where benchmarks play the key role. There are some other advances that we're making, but I'm not going to emphasize those today. I'm going to emphasize the applications. There's a lot of empirical work on the improvements in the corporate bond market that came with price transparency from transactions reporting under TRACE. I'm not going to review that literature, but it's quite interesting, and I recommend in particular the last paper I listed by Asquith, Covert, and Patak, the same Patak that Fujita was discussing yesterday. And then there's some related work on transparency in dealer markets, but farther away from search-based models, not really close to what we're doing today, but if you're interested in the subject area, I recommend those as well. Okay, so here is our setup. Actually, I already alluded to the setup. We have a continuum of buy-side. Buy-side in finance means non-dealer. Buy-side means you're in it to buy, okay? You're an outside investor, you want to buy, of which mu have no cost for finding the prices that any dealer is offering. There's going to be N dealers in the market. They're going to have prices available on their website, let's say, for selling this financial asset. Yunnan is one of the slow traders. Sorry, Yunnan, you're slow. And he won't be able to search the entire market instantly. He will have a search cost. So if he wants, this is Yunnan right here. If he wants to enter the market, he has to pay a search cost. And he can go and find a dealer platform. He can look at the price. And if he decides he wants to search again, he has to incur another search cost, and so on. Okay? So that's the slow traders. Fast traders have zero search cost, so they instantly know all the prices available. Okay. Here's a little numerical example, and I guess this is the price for maybe a bond in terms of its yield. 2.1%, 1.9, 2.2, 1.7, 2.3. In this case, well, actually, bond yields are not good because they're inverse to price. Just take this the price of an asset. In this case, if Yunnan could know, he should go to the fourth dealer and get the price of 1.7. Whereas Steve, for example, he's a fast trader. He instantly sees that the fourth dealer is offering the best price, and he will go there. The dealers may have different costs for selling the asset. And the costs are going to be a random variable C, standing for cost, which is unknown to Yanung, plus an idiosyncratic variable epsilon I, which varies across the dealers. So and these epsilons are independent of C and independent of each other. There are two different versions of the market design, one with no benchmark, in which Yanung doesn't know C or epsilon, and one with the benchmark in which Yanung sees the published cost C. Yanung can observe because Bloomberg or the Wall Street Journal or whatever, Reuters or his news, Thomson Reuters reports C on a screen. Now Yanung knows the common dealer cost C. Those are the two worlds we'll look at. One in which C is observed, that's the benchmark world. One in which C is not observed. That's the no benchmark world.
Who are the fast traders in reality?
In reality? Well, the other dealers are actually the fastest traders. They can canvass the whole interdealer market very quickly because they have an interdealer broker screen and they can see all the trades of the other dealers. Now, in this model, we're taking a continuum of fast traders, whereas in practice, there's only a finite number of dealers. Okay, that's maybe not as realistic as we would like. This is an abstract economy. What we would really like to have is a model in which there are no perfectly fast traders. There's a heterogeneous search cost going from close to zero to very high, and that's consistent with the data. But I don't know how to solve that model because of the diamond paradox. So I don't know how to do it.
There is this kind of heterogeneous search cost.
Yeah.
Everyone has positive search cost.
Yes.
Then the story will be different from this?
There is some work on this where there's, in fact, some other work by the same authors, Janssen, Pichler, and Weidenholzer, and also a little bit of work by Stahl on the case where there's a distribution, a heterogeneous distribution of search costs. But it's a bit too complicated for us to solve with the additional element of price transparency. But that's, I would like to be able to do exactly what you said in a simple model. Yes, sir. Well, let's take LIBOR, for example. What does LIBOR mean? It means the dealer's borrowing cost. Yeah. And what does it mean, let's say, in the FX market? In the FX market, it's the average cost. No, it's not constant. It's a random variable. Yeah, absolutely. It's a random variable, and C is distributed. C is a random variable distributed on some interval, C lower bar, C upper bar. And that's important. It's important that Yanung doesn't know C unless it's published, because we want to compare the two cases. Now here is a feasible path by Yanung. This will not be the equilibrium path that he will choose. But here is a feasible path. Yanung enters, he searches the first dealer, he sees the price is 2.1. He says, well, maybe I can do better. He goes to the next dealer, he sees the price is 1.9. He says, well, maybe I can do even better. He goes to the third dealer, he sees the price is 2.2. And he says, okay, well, I've been using up a lot of search costs. Let me just take the best price I've seen so far, which is 1.9, and I'll go trade there. If that's feasible, that's not going to be the equilibrium path. Now, there's something reasonably unrealistic about this assumption, but we need it for tractability. The unrealistic assumption is that when Yanung goes back to the dealer number 2, the price is still 1.9. Okay? By then, maybe the price will have changed. And there is some work on that by Haoshang Zhu in a Review of Financial Studies paper, but it makes the problem untractable. We're not going to do that. We're going to take the tractable case in which Yanung can pick the best price he's seen so far. Every time he searches, he incurs a cost S. Okay, let's look at his payoff for this particular path. First of all, Yanung values the asset by some amount V. And V is common knowledge. We can take it to be a constant. It plays no particular role other than it sets the value of a buy-side investor. So V is a constant. But he had to pay the price 1.9, and he incurred 3 search costs. So that's his total payoff. Okay? He could have chosen not to enter the market at all. He could have chosen to stay out of the market based on maybe there's no benchmark. He can't tell what the prices will be. It's not worth it. In that case, he would get 0. So 0 is the outside option. Or he could have gone to the first guy only. In that case, he would have had a payoff of V minus 2.1 minus S, minus 1S. Okay, everybody got the slow trader situation? We'll come back and we'll solve Yanang's search problem in a minute. Actually, let me solve it right now, because there's a little piece of very nice microeconomics that those of you who don't know it should learn it. I learned it in a 1979 paper by Marty Weitzman, and it's called the Pandora's problem. How many of you have seen the Pandora problem solved? A few. Okay, good. So it's worth doing. So let's solve the Pandora problem. In general, these dealers will set some probability distribution with a cumulative distribution function for the price that they offer. So this is a CDF for P1. In equilibrium, this will be a non-atomic measure, and that's going to end up being important. Dealer 2 will set some CDF F2 for the price that he or she offers, and so on. Now, without loss of generality, we're going to order the dealers from lowest expected cost to highest expected cost. Okay? That's without loss of generality, just by renumbering the dealers. And now we're going to simply use the result of Marty Weitzman in a 1979 Econometrica paper that has this beautiful, simple solution. And beware, if you think the simplicity of the solution means that it's an easy result, take a look at the proof. It's 5 dense Econometrica appendix pages, very complicated. So for those young people who have a facile mind, good mathematical skills, a nice summer project would be to find a simple proof of the following result. Okay? Which is step 1, this is Yanang's optimal, and this is a rigorous result. This is the optimal policy for Yanang when searching the market. First, enter the market if the value of the object minus his search cost exceeds the expectation. Well, we can just write the expectation of P1. If not, stay home. 2, accept P1 after entering if P1 is less than or equal to the expectation of P2 plus 1 search cost. Because this is the take it now, this is the search one more time option value. Okay, pretty straightforward. Next step, ... Let P star n be the minimum of P1 to Pn for each n among the dealers and the alternative up here is otherwise keep searching, of course. Otherwise keep searching, meaning go to dealer number 2. Take search dealer 2 next. Continue by letting P star be the best price Yanang has seen so far, except if P star n is less than or equal to the expectation of Pn plus 1 plus one more search cost. Otherwise, go to dealer n plus 1. And then continue to the last dealer. If you haven't already left the market, leave if Pn is greater than the value of the object. That's it. That's the obvious algorithm. It's a greedy algorithm. Just order the dealer's best expected price first, and keep going as long as searching one more time is better than taking the best price you've seen already. Now, this is a seductively simple solution to a rather complicated problem. And if you've seen optimal stopping theory, you might have had the intuition that as I get fewer and fewer dealers left, I should become more and more worried that I won't find a good price, and I should be more willing to accept the price that I've seen already. And that's not the case. That is the so-called secretary problem from operations research, and that's not what we're doing today. That's a different problem, and we can talk about that later if you're interested. So this seductively simple solution method is actually quite a complicated problem. It's closely related to the bandit problem, if you know the bandit problem. How many have seen the bandit problem? Very similar mathematics. Aki?
Yes. I have a question. I think this is very beautiful, but in the second step, is there any possibility that this searcher quits and decide not to search?
Once he's decided to enter the market,
Yes.
and he's gotten a price that's
Suppose P1
yeah. Sorry, this always has to be less than or equal to V. Sorry, absolutely. Typo. So this is a greedy algorithm, and we're going to be taking the case of a symmetric equilibrium in which all of the dealers quote the same probability distribution for the prices. By the way, it might seem curious to you, why would they quote according to a random strategy? Well, I said you can show mathematically, and this goes back to the Stahl 1989 paper, the dealers will never put an atom on any point. Why? Well, because the other dealers will see that. It's a common knowledge. It's a Nash equilibrium situation, and they'll undercut by epsilon. We'll give some other properties for the dealer distributions in a minute. So as I said, again, it's a challenge to those of you who think you're pretty good at problem solving to find a simple proof of this very clever result. This is not our result. This is Weitzman. Okay, so our results. First, a welfare comparison of the simple market with and without a benchmark. Secondly, when we have dealers that may have different costs, we'll show that matching efficiency is improved. That is, it's more likely that Yanung will get matched to a low-cost dealer than a high-cost dealer when we have a benchmark, because he'll be able to compare the benchmark to the dealer quotes. Number three, we'll study, well, we only have 25 minutes, so we won't be studying in any depth, but I will mention that among these dealers, they have a decision to make whether to get together and introduce a benchmark. And you might naively think, well, no, they would never have a benchmark because a benchmark will force them to compete, and their profit margin on each trade will go down. And they like high profit margins. Well, that's only one part of the intuition. The intuition that the profit margins will go down is correct, but with the benchmark, Yanung is more likely to trade, and the volume of trade will go up. So in some cases, the dealers will voluntarily create competition for themselves, reducing their profit margins in order to increase the volume of trade by even more, proportionately. And all the benchmarks that we see in practice were introduced by dealers or other market intermediaries. There's no government regulation that forces a benchmark price, or at least until recently. Now there is some attempts by regulators to force benchmarks onto the market, but historically almost all the benchmarks we know were voluntarily introduced. Next, if we have different cost structures where Aki and these three market participants as dealers have low cost, and these three guys have high costs, the low cost dealers will meet and say, you know what, if we introduce a benchmark, then there will be more price transparency. Yunnan will be able to find us as low cost dealers, and Yunnan will not trade with the high cost guys because he'll see that their prices are too high. And we will benefit by getting an increased market share of the intermediation rents, more than overcoming the reduction in profit margin on each trade. And you get these benchmark clubs. That's how exactly how LIBOR was introduced in the late 1960s by a club of London banks that said, if we provide our average cost of funds to the market, then we're going to get more business from global borrowers, because the other banks will not be able to compete with us. They have higher costs of funds. And then I know that we won't have time to talk about the incentives for dealers to manipulate the benchmark, but we do have some results in the paper on that, but I'm not going to talk about those today. So this is all going to happen in a few minutes. I'm just going to outline the results. Okay, so we just did a possible sample path a moment ago. Now we're going to consider the equilibrium behavior of Yunnan. This is his strategy. His strategy in equilibrium will be to enter, this is with a benchmark, will be to enter with a probability lambda c that depends on the benchmark. So lambda depends on c, the benchmark observation that Yunnan makes. Okay, again, c is published, average dealer cost. Yunnan sees that, he enters with probability lambda c. It's going to be a mixed strategy equilibrium. Then he's immediately going to accept the first dealer offer that's below some reservation price that Yunnan has in his mind, which is RC. And the dealers will be able to calculate what Yunnan's reservation price is, because we're going to give you a closed form solution for it. And so they're only going to quote at the reservation price RC or lower. Okay, they will never offer a price higher than his reservation price because they'll lose the trade and they'll lose all the rents. So they'll always offer below RC. How much below depends on their strategy, which we'll get to. And again, this is one possible sample path where Yunnan's reservation price is, let's say, 2, and therefore he buys from the first dealer that's offering a price below 2. Now we're going to exploit, we have a continuum of investors. We're going to exploit, actually, Yunnan is an appropriate investor because we're going to exploit his JET 2006 exact law of large numbers so that when we average across population behavior, we get almost surely the expected behavior of any one agent. Okay? Well, of the slow agents, the average cross-sectional behavior will be equal to the expected behavior, and for the fast agents likewise. And that will allow us to compute the solution explicitly. So this is, again, a bit unrealistic, quite unrealistic, but as an abstraction, it makes the model very tractable. Okay. As I already mentioned, the support of the distribution of dealer cost is some interval. We're only going to look at the equilibrium on the interesting event in which the cost is low enough that it makes it worthwhile to Yunnan even consider to enter the market. Because otherwise, everybody knows that none of the slow traders will enter. We'll have only fast traders. And if there's only fast traders, all these dealers can do is Bertrand compete. They have no source of rents. I already mentioned that the unique symmetric distribution F has no atoms, and that its upper support point is the reservation price of Yunnan, which we haven't calculated yet. So there's two constants to calculate. One is the lambda c, the probability of entering. The other is the reservation price RC. And we also have to calculate the probability distribution of dealer quoted prices, F. Those are the three solution objects. And those are all coming explicitly. Okay, first, we're going to take what's going through Aki's head when he sees some trader approaching his platform. And he doesn't know that Yunnan is fast or slow. In fact, he's just posting a price. He's taking any traders that come to his platform and want to lift his offer. Okay, so he has to first calculate what's the probability that someone visiting my platform is a fast trader. Well, that's an easy calculation because the probability Q of being a fast trader is the mass mu of fast traders divided by the mass of all traders visiting Aki's website. He knows that every fast trader will eventually get to his website. He also he needs to know what fraction of all traders are fast. That means he needs to divide mu by the total mass, which is mu plus the mass of slow traders that get to his website. What is that mass? Well, the slow traders are starting, because of symmetric equilibrium, at a randomly chosen dealer. So there's only 1 over n of them that will get to his website first. They also don't enter with probability 1. They only enter with probability lambda c. So we have 1 over n times lambda c. And then finally, we have to multiply by the mass of slow traders, which is 1 minus mu. So the denominator of Q is the total mass of investors that get to Aki's website. The numerator is the total mass of fast traders. The ratio of the two is the probability of a fast trader. I'm going through this very carefully because it's important in order to understand the next equation, which is the central equation in the stall-based theory of over-the-counter markets.
So the dealer can tell whether this is the fast?
No, I forgot to mention one important fact. In equilibrium, Yunnan is going to end up accepting the price on the very first platform that he approaches. In the case where there's a benchmark, with probability 1, he's going to end up accepting.
So this is a paddling.
Yeah. And we know that's true because these quote functions have a support which is below RC. So we know with probability 1 that Yunnan is going to end up in equilibrium accepting the first dealer quote. So that's why he knows that the dealer knows that he gets 1 over n of all the slow traders. Okay, so now, as I mentioned, if you could just focus on, I know this is dense notation here, but if you could just focus on the next equation, then the rest will be very, very simple. Okay, the next equation is Aki's strategy for where to put the probability mass on his quotes. So remember these. This function f, let's plot its density. Its density is some thing which it lies below Yunnan's reservation price. And Aki has a choice of how much probability mass to put here, how much probability mass to put here, how much probability mass to put anywhere. It's going to, by the way, have a density, as we'll see in a minute. So now you can think of Aki as shifting as a calculus of variations problem. He can shift some of this mass over here. He could shift some of this mass up here. And he's going to keep shifting probability mass around until the marginal value of adding probability mass at any one point is the same as the marginal value of adding probability mass to any other point. Okay? So that's a very simple solution. It's, again, a greedy algorithm. That means that every point in the support of f, every point in this support must have the same expected rents for Aki. Because otherwise, if one point had a bit higher expected rent than another, he would shift some probability mass over. Okay, so That means that all we have to do is to equate the rent, the expected rent of Aki at 2 points. The first point is the expected rent at the upper boundary where Yanung is just indifferent to taking the trade. Okay, that's the right-hand side of this equation, the second equation down. I think I actually have a pointer here somewhere. That's the rent that Aki gets for putting probability mass per unit of probability mass at the point RC. Let's calculate that rent. Well, first of all, he's charging the price RC at the upper boundary, but it costs him C to get the asset. That's the definition of C. It's the cost to the dealers. So this is the profit per unit traded, but now we have to multiply by the mass of investors at the margin that are trading at that point. Well, the only investors that would accept the price RC are the slow investors. They have mass 1 minus Q. Because the fast investors will go to the cheapest dealer with no cost. And because there's no atoms in this distribution, if Aki happens to quote RC, with probability 1, there will be a dealer quoting at a lower point. So Aki will get 0 fast traders at the upper boundary. That's the right-hand side, average rent for quoting the price RC. Now on the left-hand side, we're going to put the expected rent associated with an arbitrary quoted price, P. Any price in the support of F. Call that point, that support point P. We're going to calculate the expected rent at that point P, and we're going to equate the two because they have to be equal everywhere in the support. Okay, on the left-hand side, first of all, well, let's do the profit margin first. If he quotes the price P, then his profit margin is P minus C. And now all we have to do is multiply by the mass of investors that would take the price P. Well, that's easy. Every slow investor, that's the mass 1 minus Q, will take the price P because it's below their reservation price. So the first term, 1 minus Q, is obvious. Now let's talk about the fast traders. I think Steve was one of our fast traders. There's mass Q of them, but they might find a better price than P. So Aki is only going to win that trade with the probability that the price P is the best available among N dealers, all quoting with the same distribution F. Well, that probability is 1 minus F to the N minus 1. There's N minus 1 other dealers. 1 minus F to the N minus 1 is the probability that P is below the prices of the other dealers. So that's the mass of fast traders that take the price P. Here's the mass of slow traders that take the price P. Now we can equate the left-hand side with the right-hand side and get a closed-form solution for this CDF F. Isn't that nice? Well, we have two missing constants, lambda C and RC. We're going to deal with those in just a second. But we have a solution now up to 2 constants. Okay? And there it is right there. Now we have to calculate the constants. One of the constants we get from Weitzman's solution, which says the upper boundary price is defined by indifference, which says the value to Yanung of accepting RC, the highest price he would accept must be equal to the value of searching one more time. That was the Pandora solution, which said keep searching as long as you haven't gotten to the next best expected value. And so just at the margin, you're indifferent. That defines an equation for RC. We can now solve it. RC is equal to this expression, which has a bit of an ugly constant in it, alpha, but that's okay. There's an interpretation for alpha, but I'm not going to have time for it today. There's one other missing constant, lambda C. Now that we know everything else, we can solve for lambda C by solving this equation. And this gives you a solution for lambda c if it's interior. If the solution of this equation gives lambda c less than 0, then take lambda c equal to 0. If the solution for this equation gives lambda c greater than 1, then take lambda c equal to 1. Otherwise, lambda c solves this equation. Okay, so now the model is completely solved, and we can examine its properties. Properties that we're interested in are the ones that I gave you, which are welfare. They're all welfare related. And we're going to do those, at least a summary of them, in the next few minutes. Any questions before I move on to the welfare properties? Okay, here we go. Oh, I forgot to compare with the case where there's no benchmark. So let's do that very quickly. In the case where there's no benchmark, now the probability that Yanong enters can't depend on C. It's just some constant lambda. And it will turn out that he will accept the offer on the first platform if it's below his value. If it's not, he will leave the market. That's the equilibrium. So in this sample path, Yanong enters. He sees the price 2.1. Because his value is less than 2.1, he leaves the market. Okay? That's the solution. And now we do the welfare analysis. This is going to take another minute or two. I don't want to crowd out discussion time. Yes?
So what about the solution before? So that's
yes.
for the whole, like you mentioned the dealer might have different costs providing liquidity.
Yes.
And here the assumptions they have the same.
Here it's common cost. We're going to get to the heterogeneous cost case in just a minute. Sorry, I should have clarified that. Okay, so in terms of welfare, in order to analyze welfare, let's change variables from the cost C, which is an unknown cost variable, to the gain from trade, which is the maximum of value to Yanong minus C and 0. That's the gain from trade on every possible trade. Okay, that's the variable, that's a random variable of interest. And we're going to let big lambda of x, this new variable, be equal to lambda c just by using this equation. And now we can calculate the social surplus, which is the total gain from trade. W as a function of x is the mass of fast traders times the gain from trade, plus the probability that a slow trader enters times the mass of slow traders times the gain from trade minus S because the slow traders incur one search cost. Okay, so that's the total gain from trade in equilibrium, which depends on all the parameters of the model. It turns out, and this is a fairly straightforward calculation, again, I gave it to my students as a homework, but it turns out that in the case with no benchmark, the total social gain from trade is the same function W evaluated at the expectation of X. And now it kind of looks like I'm setting you up for Jensen's inequality. I want to compare the expectation of W of X with W of the expectation of X. Because the expectation of WX is the welfare with a benchmark, and W at the expectation is the welfare without a benchmark, and the larger of the two wins. It's not quite the same as Jensen's inequality, but it will turn out to be morally very similar, because it turns out that this function under simple parametric conditions is subdifferentiable. What does that mean? It's subdifferentiable at the expectation. In other words, this is the expectation here. The function W looks like that. It's not convex. It has a point of concavity right locally here. But there's a hyperplane that supports W at the expectation. And now you can use the subdifferential inequality. Just average using the subdifferential or supporting hyperplane, and you get, under mild parametric conditions, that the social value of having a benchmark, which is the expectation of W, the average across the distribution here of the big thick black line is higher, as you can see, if you just average that function, it's higher than W evaluated at the average. Okay, so the value of having a benchmark. Now let's see economically what's the intuition. The intuition is X is the gain from trade With a benchmark, whenever the gain from trade is high, Yanung is more likely to enter the market. Whenever the gain from trade is low, Yanung is less likely to enter the market. With the benchmark. Again, with the benchmark, if there's a high gain from trade, Yanung can observe the benchmark. He can say, I should be entering. He goes into the market. He gets the gain from trade. When the gain from trade is low, that's because the cost to the dealers is high, and he can observe that. He says, I'm not entering the market. So you get the gains from trade exactly when they're high. You don't get the gains from trade when they're low. And that's good. If there were no benchmark, then Yanung would have to base his decision on his expected gain from trade, and that's not good. Okay, so that's the intuition. I'm going to skip the counter. There is a counterexample for weird parameters. Matching efficiency is just what I said. Let me remind you what matching efficiency has. I'm not going to have time to go through this. Matching efficiency says you get more trades with low-cost dealers when there's a benchmark. That's a pretty simple statement. And again, there are some parametric conditions which are quite reasonable under which that's true. You asked about the heterogeneous case. That's the main result for the heterogeneous case. Back to the homogeneous case, if the dealer profits are in a certain region, then they will want to have a benchmark, and we know it's socially efficient for that to be the case. If the dealers don't want a benchmark, it doesn't mean that you should not have a benchmark. It means socially you might want to have a benchmark. Okay? That is, even if the dealers choose not to have one, a regulator might benefit the market socially by introducing a benchmark. And that's exactly what some regulators have been doing in Europe and the United States just recently. They've been forcing new benchmarks into the market. Last thing that I'll mention is the result I mentioned earlier. If these dealers have low cost, then they will say, let's have a benchmark. These dealers over here, one of whom has already left, will say, no, we don't want a benchmark, but they're going to get outvoted. The benchmark will be introduced. The low-cost dealers will drive out the high-cost dealers. The market is going to end up being more efficient because all the trades will occur with low-cost dealers. I'm not going to have time for this. Let me just remind you, this is OTC markets. If we had a central limit order book, which I mentioned yesterday, it could be that we're all better off, but the dealers might not want to migrate to a central limit order book because then they would lose a large fraction of the market. So dealers in general tend to prefer not to have a central limit order book market. Did I mention yesterday that there was a litigation in which the dealers were alleged to have colluded to prevent the entry of an exchange? Yes. They settled that case last year for $1.8 billion. I was one of the experts. And the discovery was quite interesting. Currently, we don't have, in many OTC markets, an exchange. We have a platform on which multiple dealers can bid. That's now regulated in the United States and in Europe under new regulations that you have to have a platform if you don't have an exchange. Unfortunately, there are multiple platforms, and that's not efficient. That's bringing us back at a kind of meta level to the search problem we just faced. You can solve this problem using the same techniques that I just described. A little bit more combinatorics involved, but it's a straightforward problem to solve, and it has been solved. There's a paper by Sebastian Vogel at EPFL in Lausanne. Reducing fragmentation helps. That is putting more trade on the same platform. In fact, empirical work by Ananth Madhavan and Terry Hendershot shows that if you, on the horizontal axis, if you have more dealers quoting on the platform, the expected cost to the investor goes down quite a bit. This is for the corporate bond market. This is the last slide. It just shows you the current market structure. This is the current private solution for market design, which is the dealers have a central exchange, but the non-dealers either trade bilaterally with dealers or on a platform. So we just ran out of time. I'm sorry that I used up all the time. Thank you.
So we have no time, but if
Thank you, Aki. Thanks for being the dealer, too.